Okay, there's another basic principle. Now, there are some conditions that I don't mention here. The altitude has to be perpendicular to the base and such, but the basic principle is if it comes to a point, the volume's 1/3 of what it would be if the cross sections were uniform. And what I'm thinking of is like a pyramid. And I've sketched a pyramid here. We see that we have a rectangular base. The pyramid doesn't have to have a rectangular base. It could be any polygon. But we have a pyramid in this case that has a rectangular base and it has some altitude. And by the time it gets to that altitude, everything has come to a point. So that's the nature of a pyramid. And when that occurs, the volume of this pyramid is going to be 1/3 of what it would be if the cross sections were uniform. If the cross sections, excuse me, were uniform and equal to the base, maybe I ought to put that down. Okay. Cross sections are uniform and equal to the base. I really should say congruent to the base, but I'll live with this. This is an approximate statement. It's kind of a rule of thumb. Okay, so if the cross sections were all equal to the base, what would we have? Well, we'd have like a stack of bases here. We'd have like a box, a rectangular solid, and I've indicated that by the yellow dotted lines. People said they could kind of see that. And I haven't really done that great a job of it. The peak should end up about here. So this side, all these sides should be a little shorter, but that's okay. Okay, you get the idea. This pyramid can fit inside this rectangular box. So if we apply the principle, then the pyramid's volume should be 1/3 the volume of that box. Okay? Well, what's the volume then of a pyramid with rectangular base 4 centimeters by 10 centimeters? That'd be like 4 here and 10 here. And altitude 15 centimeters. Well, that's easy enough. If we calculate the area of this box and take 1/3 of that, we're going to get the area of the pyramid. So here's the statement. Volume of the box is area of the base times height. The base has dimensions 4 centimeters by 10 centimeters. That's going to give us 40 square centimeters. We multiply that by the 15 centimeter height and we get the 600 cubic centimeter volume. So the volume of the pyramid is what? The volume of the box is this. Volume of the pyramid is 1/3 of that, or 200 centimeters cubed. So we can generalize this. A pyramid with base area B and altitude H has volume 1/3 the area, 1/3 BH, B being the area of the base, H being the height. And that's illustrated by this example. We could also write the same relationship for cone with base area B and altitude H, because a cone comes to a point the same way a pyramid does. It's just that the base of the cone is circular. So if you have a cone, you're going to have to find the area of the circular base, but that area is going to can be represented by B. Altitude is H, so we can write again, volume is 1/3 BH. Now, the way you usually see the formula for the volume of a cone, it's written 1/3 pi r squared H. Okay, that's a little harder to remember than this, and if you just use this principle, this is really pretty much unnecessary, and of course it's pretty much easy to derive anytime you want it anyhow, because what? The base is a circle of radius r, so its area is pi r squared. So the area of the base here is replaced by the pi r squared, which is the area of the base of a cone with base radius r. Okay, so there's no great mystery to this formula. It's really just a version of this formula.